Good afternoon, Math 146. As promised, I wanted to just summarize some of the probability stuff that we didn't get to at the end of class. I'm speaking to both my sections of the class. So if you recall, Google will let you do this dice rolling program with any number of multi-sided die. And I chose this because it allows us to play with dice in a way that you probably haven't before. And I think both classes got through the creation of all the possible outcomes, focusing on the fact that rolling different numbers on a six-sided die and a four-sided die would create 24 different possibilities. This is called the sample space. And the highest you could roll is a 10, the lowest you could roll is a 2, but it's also the least likely that you could roll a 2 and a 10 because there's only one combination of dice that results in a 2 and only one combination of dice that results in a 10, whereas multiple combinations of the dice can rolls 5s, 6s, 7s. Those all have equal probabilities, 4 out of 24 for rolling a 6, 5, 6, or a 7. So in that case, there are 4 ways to roll a 7. 4 out of 24 works out to be about a 16.7% chance of rolling a 7. And the probability of rolling not rolling a 7 would be the complement of that, the remaining 83.3%. So I think we all got there in class. The Wednesday class did not get to any actual rolling, but the Thursday class did. So what you're looking at here is the combined data across 5 different groups, each of which we're able to roll the dice 50 times and gather the data. So again, remember that 2 and 10 are the most unlikely rolls. So what we would expect is the fewer rolls of 2s and 10s. Actually, you can kind of see this: 15, 21, 31, 47, 40, 37, 31, 21, 7. This sort of more and more and then less and less. This worked out pretty classically. But what we're looking at on the right is called an empirical probability, which is kind of like saying, we don't know how these dice work. We shouldn't assume that rolling a 1, 2, 3, 4, 5, 6 is equal probability for each of those. So the only way we could really have reliable data is to conduct an experiment. So between us, we roll the dice 250 times, and the probabilities work out like they do on the right. About 6% of the time, the class rolled 2s. About 8.4% of the time, they rolled 3s. 12% of the time, they rolled 4s. And then the most common rolls, 18.8% on a 5, 16% on a 6, 114.8% on the 7, 1.2%. Oh, I think that might be a typo. That's supposed to be 12% on the, no, it's not. We already have this. Oh, no, it is 0.012. Sort of surprisingly small amount of 8s. And then there's got to be an error there. I think these are both 0.12, not 0.012, 12% as opposed to 1.2%. And so on and so on. So what the next thing really gets to is the empirical probability of rolling a 7 is about 14.8%, even though the theoretical probability was 16.7%. So notice those numbers are close, right? If we were to roll these die infinite times and they were truly fair, then we would expect to have exactly 16.7% empirical probability. The empirical probability would become the theoretical probability. So a couple of probability rules. If you're talking about the separate disjoint outcomes, as in the probability of rolling a 6, 7, or 8, and you can't do both at the same time. Basically, you can put those probabilities together. It's kind of like you win the game as long as you roll a 6, a 7, or an 8. Like, all right, there's lots of ways to do that. In fact, there's 11 ways to roll a 6, 7, or an 8 out of the 24 possibility. So it turns out that that's about a 45.8% chance that you'll roll a 6, 7, or 8. So notice when we talk about this or this, an event of one event or another event, that those addition is what's used. And that was for the theoretical probability. The empirical probability is the same idea, that we take the empirical probabilities and add them together. 40 out of 250, and those are the actual rolls. 37 out of 250, 31 out of 250. The class collectively rolled 108 6, 7, and 8s out of the 250 rolls. So that's about 43.2% of the time. Again, the theoretical and the empirical very similar, even though they came about in different ways. The theoretical probability of rolling 3 7s in a row, this came up in class, but when you're talking about you need 3 things to happen, all 3 of them happen, you need this and this and this, that's very unlikely that you would roll 3 7s in a row. In fact, it's 1 out of 216. There's about a 0.5% chance that you would roll 3 7s in a row. So main idea is just defining theoretical and empirical probability and start to get introduced to some of these probability rules when you use addition, when you use multiplication. All right, I'll see you all next week.